All right, well then, good morning. So this is the second lecture. So last week we talked about performance in general. Okay. We learned that to report the performance, we prefer to use speed up. All right? And speed up is actually a ratio. This is a ratio. So to calculate the average, we have to use the geometric mean because this is a ratio, there is no unit at all. All right, so we go with geometric mean. And we have learned that if you run several benchmark comparison, let me try to move this thing out. Oh, sorry, this one. Okay. Let's just hope it does. Yeah, better. And we learned that if we have several comparison, several benchmark, we have to combine them somehow. All right. And we learned that if we always use ratio, use geometric mean, we learned that even though we compare B to the baseline A, we compare C to the baseline A. If we divide the geometric mean, we also got the same number. It's as if we compare B to C, and I take a note last week. This should be A. Sorry, that's typo. Okay, that's about the geometric mean, the benchmark, and things like that. And then we move on. We move on and say, well, if we only focus on the CPU time, in a sense, when you run something on your computer, CPU do something, but also you have to spend time on others, like memory time, the speed of your disk drive, the speed of your typing, like that. So if we only focus on the CPU time, we say we can just do calculation. We can do calculation. And toward the end of last week, some of you asked me, hey, what is the cycle time? What is the period? So let me clarify that a little bit. Well, technically speaking, you should learn that from other class, other course. I seem to remember that Professor Yang Zhao used to taught you about the finite state machines and logics. But anyway, if you cannot remember or somehow you didn't know that, let me clarify this a little bit. So it's like this. You put a clock into a processor. The clock would look somewhat like this. One period of clock, we call it one cycle. That's one cycle. So rather than say how many seconds does it take to perform an instruction, we would say how many cycles. Like some instruction may say we need 3 cycles, so it would be 3 cycles like this. This is 3 cycles. So if it takes these 3 cycles to perform an instruction, we would say, oh, CPI is 3, meaning it takes 3 cycles per instruction, like that. So if every instruction takes 3 cycles, and we have what? N instructions, so it would be CPU times equal N times 3. right? Assumption is every instruction use 3 cycles. We have an n instruction, so it's n times 3. But again, the unit would be in cycles, right? Cycles. And we didn't want that. We want the unit to be like seconds. That would be the time that we want to measure. So we have to know the cycle time, meaning how long does it take for a clock to have 1 cycle. That's the cycle time. And when you say that your processor is something like, let's say 1 gigahertz, what does it mean? That means in 1 second, we have what? 10 to the 9 cycles. So 1 cycle would be what? 1 over 10 to the 9. That would give you seconds. Right? A better way is to report it in nanoseconds. What is nanosecond? You know, micro, nano, pico, you know those prefix, right? Same things. Right? So this is how we come up with CPU time, meaning we can just do calculation. We know the clock speed. We know that the instruction would take some number of cycles to process. Giving an instruction, you can just do calculation. All right, so this is how we come up with CPU time, by counting, by the simple calculation. Okay. And yeah, that's basically the things that I explained. And for some processor, it can be that we have CPI equals 1. So that the speed of the CPU would likely depend on the gigahertz or megahertz of clock that we put in. Just like that. But in reality, it's not always like that. We do not have just 1 cycle per instruction. It can be that some instruction would take 5 cycles, some instruction may take 3, some instruction may take 8. Another way to do it, you do the average CPI. So when you write software, like when you do in embedded system programming, the one that you took on the first year, you would write some code like you load something, oh, maybe this is 5 cycles. You add something, oh, maybe that is 3 cycles, something like that. So each instruction have different cycles, different number of cycles. And if we know that, oh, we do the load, I know maybe 30% of the time. We do the add, maybe 50% of the time. We do other complex calculation, maybe 20% of the time. So you can just find an average. This is basically weighted average. Yeah. Right. Just weighted, just like that. So we can just estimate the CPU time doing simple counting. How many instructions do we have? do simple average CPI and do the math, put them together. I think we did this one last week, right? We already did this question. Okay. So let's try another one. All right. This is tricky. I mean, this question is a little tricky. Why? Because it's designed to report the performance using the MIPS unit, which is a bad unit, but back in the past, sometimes the vendor, the CPU designer would report performance using the MIPS unit. So this exercise, I ask you to do some calculation in MIPS unit, and you will find that it doesn't always mean high number in MIPS is a better performance. It's not like that. So let's try this. I say we got two computers, A and B. Different CPU, different architectures, completely different things. And CPU A say, my CPU can do 10 MIPS. MIPS mean million of instructions per second. So it's a combination of CPU time and CPI in one number. Okay. And CPU B say we got 9 MIPS. And they say CPU A running at 33 megahertz, CPU B running at 20 megahertz. If you compile a software, a piece of program to computer A, it would take 12 million instructions. And for B, it would take 10 million instructions. So maybe I highlight it with different colors. That would help you a little bit. Green for B, blue for A. Okay. All right. Now, question is simple. You have to pick one. Which one is faster? How would you answer this kind of question? Calculate. Calculate? Yeah. How? Yeah. So technically speaking, you want to say which one is faster. So you have to convert the MIPS, the megahertz or whatever into seconds, right? How many seconds does it take to run this piece of software on computer A? Same question. How long does it take to run this piece of software on computer B? If you can find the time it takes, then you can say which one is faster. The small number means faster, right? That's what we have established. Okay, let's try. Since I already do some calculation for you, so maybe I just explain it. Computer A in blue, okay? Computer A says 30 megahertz. So convert it to seconds would be what? 1/33 times 10 to the 6. This is the cycle time for computer B. Sorry, computer A. Okay, we got the cycle time for computer A. And we learned that CPU time is a function of instruction count, CPI, and cycle time. We already got the cycle time. Okay. And this processor decides to tell you about CPI in MIPS unit. So 10 MIPS mean 10 million instructions per second. You have to convert to how many cycles does it take to run this single one instruction. So it's 10 million instructions times the cycle time 1 over, that would give you basically the CPI. So this is the CPI. Okay, and we do simple calculation. Oh, we got what, 12 million instructions. It should be 33, like maybe a typo. All right, and this would cancel out and give you 1.2 seconds. Right? So you compile software, run it on processor A, it would take 1.2 seconds. Now do similar calculation for computer B. Again, the clock is what, 20 megahertz. Convert megahertz into cycle time in seconds. If you want to do the math, it would be 5 nanoseconds. But anyway, I would leave it like that. And then find the CPI. Again, this processor decides to tell you about CPI in MIPS. So it's 9 million instructions per second. You time the cycle time, you would get the cycle, and it would give you cycle per instructions, right? Again, this would be cancel out. So you got 1.1. Which one is faster? B, right? B is faster. So give me the speed up. That would be 1.2 divided by 1.1, that would be 1.09. Speed up. So let me specifically point this out. From the number, you say, oh, A is faster, that's 10 MIPS, right? B should be slow, it's only 9 MIPS. Is it a good unit? No. But back in the 70s or 80s, they advertised in MIPS unit. Intel would say, oh, our processor is, I don't know, maybe 10 MIPS, 20 MIPS, something like that. And Motorola would come out, oh no, we only got 9 MIPS. But at the end of the day, Motorola CPU might be faster. Because MIP is not a good unit in a sense. All right? Better? Better than last week? Yeah, last week some of you kind of, I don't know, confused, panicked at the end of the class and say, oh no, we are in trouble. Again, this is grade school math. But you have to figure out, oh, it's just this function would give you something. Then play with the number a little bit. Are we good? Okay. All right. And then we move to arm down. Again, toward the end of last week, of our last class, I tried to establish the idea of arm down for all. And I use this symbol chart to explain. Let me recap this again quickly for those of you who might miss the concept. First is like this. You want to do something. In this example, I say go shopping. And there are several steps that require to do that. Right. In this case, the green is for the time that you have to drive from A to B, for example. And the blue is the time that you take in the supermarket, do the shopping. I say I want to make it faster. If you can invest in just one, like the first choice, make the green twice faster. That means the blue would still be the same, right? Or the second choice, you cannot drive any faster because of the traffic or anything, but in the supermarket, you say you do 5 times faster. Quick shopping, run and grab thing. So this is twice faster. This is 5 times faster. You see the result. Which one is better? Right? And technically speaking, just make it twice faster should be easier to do. Not always, but should be easier to do. And that's the same idea that we use to improve our computer. Like, oh, we spend most of the time reading from the memory. Maybe we make our memory faster. Just twice faster, maybe. And we got good gain of performance. Easier and better than making the CPU do the calculation faster. Or one way to say it, Amdahl say it's a law of diminished return. You put in 5 doesn't mean you get 5 times better. You put in 2 twice doesn't mean you get twice the performance. It's a ratio of which part that you are putting in, and it accounts for what. Or another way to say it is that if you want to improve something, you should make the common case faster, right? I spend the time doing the green, so make the green faster. Most of my time with the green, so I make the green faster. Make the common case fast, like that. And we do that in our computer as well. It's slow. Where? Which part is slow? And you always see speed up in a graph like this. So for example, in this graph, this is the number of processor. This is the speed up. You would see that, oh, it would saturate at some number. Why? Simple. If you say that in the blue, you can parallel, for example, but the rate you cannot parallel. That means even though you can make it 100 times faster, it's still limit. You cannot make the rate smaller. So it would saturate at somewhere. Not every part can be parallel. That's the point. Got my point? So regardless of what you're trying to do, the speed up would always limit somewhere. Okay, similar things. Let's say now you move next to the supermarket. You don't have to travel, so you don't have this. No more traveling. But you still have to do shopping. You cannot make it any faster. So it would saturate somewhere. That's the unbound. Okay, and just to put it into a formula, it would look somewhat like this. If the original time is 1, so it's like this. This is 1. You make some path faster by n, so you divide this by n. This part still stay the same. Okay, maybe I change the colors. So speed up would be original time divided by enhanced time. This is the original time, make it 1. All right. The enhanced time would be this part divided by n, and this part stay the same. So this is the part that stay the same. This is the part that divided by n. Get the number. So if you ask me whether you have to remember the Amdahl formula, the equation, I would say no. Just standard speed up. Okay, good. Let's see an example. Okay, before we get to an exercise, let me recap this equation a little bit. Now that we know that CPU time is a function of instructions, CPI, and cycle time, I say, let's make our CPU faster. How? You basically have to minimize this function, right? How to minimize this function? What would make the number of instructions smaller? You have to redesign the instruction set, maybe, but most of the time you cannot do that. Another way is find better compiler, find better logics that you would use less number of instructions. If possible, so let's go here. So that means you got piece of code, maybe in Java or maybe in C. Use different compiler would give you different number of instructions, meaning different performance. Okay. And believe it or not, in case of Intel processor, It used to be that Intel didn't make the best compiler. Other company can make better compiler, and they sell it for $1 million in the past, millions of dollars. Yeah. And later Intel decided that we will buy that compiler back. So I got a case that I got open source software and I used the free compiler. I got decent performance. I changed the compiler to the one that Intel brought. Oh, 5% faster without doing anything. Just change the compiler. Because different compiler may have different optimization, meaning different number of instructions. Yes. GCC, yes, GCC. How about CPI? If you want to make it smaller, how? Well, that depends on the designer of your processor. But this part is easy. You want to minimize the cycle time. How? Make the clock faster. Well, the proper way to make the clock faster is that you have to redesign the internal organization of the processor so that you can put faster clock, or you can cheat by do overclock. So when someone say he do overclock, that means they try to put faster clock into the CPU, which it may fail. On my point, because the CPU may design to work at, I don't know, 2 gigahertz. And if you try to put 3 or 4 gigahertz in, that means it may fail on some instructions. Which one? We don't know. And another thing is, if you put faster clock into the CPU, it may get overheated. So sometimes you can, if you want to do the overclock, you have to put super cool coolant system into it. And we used to have a CPU that have to be cool with liquid nitrogen, with water pump the water in to make it cooler. Whether it's a good idea or not, I don't know. But that's a bad idea for portable computer. If you have to use liquid nitrogen, so pump in the water, and you want to carry mobile phone with water pump, no. So I would say overclock is a bad idea anyway. Unless you want to do it for fun, learn something, okay, that makes sense. Use it in real life? Maybe not. Any of you overclock your computer at home? No? You can try, but beware that you may break something. And don't burn your house. Okay. All right, let's do some exercise. Okay, I let you think about this a little bit before I guide you. Let's say you want to buy a new mail server. The new server would be 10 times faster, only for the email computation or the mail application. If the computation of the mail is 40% of the time. And another 60% is for the I/O, basically network, memory things. Say we buy this mail server, the new one. What would be the overall speed up? Well, this is basically down law. We improve something, we cannot improve everything, right? We cannot make the internet faster, but we can make our mail server faster. Now what? Okay, think about it a little bit. Well, I got a random question actually. If you can choose, you would prefer morning class or afternoon class? Or neither?
I mean, if you say neither, I say neither too.
How about morning? Either morning or afternoon? Which one?
Morning.
Morning better?
By my standard, morning basically just prefer waking up rather than just to commute like or I don't like commuting in the weekday.
Uh-huh.
Prefer commuting.
I don't know. I find that if I have to do class in the morning. Well, we used to start class at 8 o'clock in case you don't know. At here,
Still do something.
yeah. We used to start class at 8 o'clock. And when I walk to the class at 8 o'clock, how many students?
5.
Less than 5.
5.
Mhm. So I decided that I move my class to 8:30. Now I come to the class,
7.
oh, no lights on. But wait, I turn on the light, 10 students in the class sleeping. So we moved to class to 9 o'clock. I walk to the class, oh, maybe 10 or 20 students from hundreds. So I don't know which time is best for the class. Okay, you can do it. This one? Easy, right? You think you got it? Okay, give it a try. Okay, let's try. We ask for speed up. That basically the original time divided by enhanced time. The original time would be, let's make it, yeah, let's make some number, 100. Okay. Just to make it easier, make it 100. The enhanced time would be what? Oh, 60% that we do nothing, plus 40% that we can make it 10 times faster. Right? So what do we get? It's 100 over 64. You do the math.
Calculate. Yes, this is actually answer this simple.
If my memory serves, it should be 1.25 something, right? 1.56, sorry.
1.5625. I think your memory serve, but okay.
Got it? Pretty simple, right? This one. Okay, try this. Similar things, okay. But now let's change to the instruction class. Let's say we got a new GPU, new graphic processor. If our new GPU is 1.6 times faster, what would be the overall speed up? Know that floating point instruction is just half of the time. FP is for floating point. Okay, this one also easy. I let you do it a little bit. Okay, got it? Same thing, right? Speed up equal original time divided by enhanced time. What would be the original time? Okay, let's do some drawing then. Let's say this is the original time, right? And half of the time is for floating point. Other is for something else. We didn't change this part, but we can make it faster by factor of 1.6. Which one?
The fraction.
Oh, sorry. Original. Yeah, too small.
Original over.
Sorry for my handwriting. It's difficult to write here anyway.
Okay.
So that would be, let's make this 1. So this would be 1 over what? The part that you didn't do anything. That would be 0.5. And the part that you can make it faster, 0.5 divided by 1.6. 1.6. So yeah, you do the math.
Here, give you one analysis, 1.23, like very small, it's quite very small.
1 point what?
2.3.
2.3.
And you can get like 1.23.
Yeah.
It's the answer right here.
Okay, thanks. Just stay with 1.23 then. Okay. And that's why we call it law of diminished return. You see, our GPU is 1.6 times faster. We only got 1.23. speed up. The GPU itself is 60% faster. But the overall speed up is only what? 23%. You do not always get what you put in. That's my point. Effort that you put in only apply to certain part, not every part. I should write what divided by 1.6, yeah, to avoid confusion. Good. Still easy, right? Let's make it a little more difficult. Put it in the context of CPU time. CPU time equal what? Number of instructions times CPI times cycle time. Yeah, I just should write cycle time with TC. Okay. Okay. I'll let you think about it a little bit. Again, this is nothing compared to what you will find in the examination. This is simple, nothing. If I put something like this in the examination, that would look down to you. Not a good idea. What? Much more complex, of course, because in real life, it's much more complex. Yes. No calculator. Use your brain. Come on, this is grade school. We don't need calculator. Yeah, you got the point. Got it?
Yes, we calculated one.
Anyway, in the examination, you can leave the answer as a fraction. I'm okay with that. I don't need the exact number. I just want to see how you do the calculation. Good. Can you do it? Yes. Your colleague say finish that. How about you? Okay, I show you how I will do it. So it's like this. The original time would be like, let's say we got n number of instructions, okay? N number of instructions. Just put n here, okay? Okay, and they say 25% is for floating point. The other would be what? 75. So it would be 25% of n use 1.33 cycles, right? And 25% of n would use 4 cycles, right? This would be the number of cycles for this piece of software. Altogether, time, the cycle time, but it doesn't say what is the length of your cycle time. So let's leave it like that. Now they do some improvement. Enhance. Okay. Again, we got 75% of n. Time 1.33 because we didn't do anything to it. But for the floating point, which account for 25%, we changed that from 4.0 to 2.5. Right? And that would be number of cycles, change it 2 seconds to get this. Okay? Say that again. C. Oh, cycle time. Too lazy to write cycle time. So just use TC. And we ask for speed up. So speed up equal this one divided by this one. So it would be this one divided by this one. TC would cancel out. So what do we get? Well, actually, N would also cancel out. Okay, you do the math. Okay. Should be something like 1.23. Okay. So that's the performance thing. Let's move on to another topics. Okay. Oh, okay. Maybe I give you 10 minutes break before we start new topics then. Go refresh yourself a little bit. We're gonna start a new topics. New concept, okay. Okay, we move on to the next chapter, which is instruction set architecture. ISA for short. All right. Well, last week, I told you that instruction set architecture is some kind of abstraction. It's how the software see the computer. It's also a reference implementation for the hardware designer or the architect to design a computer that would meet the same function. So it's abstraction in a sense. Yeah. All right. Anyway, if you were to took this class in the 50 or 60, the computer architecture class would basically means computer arithmetic class. They would teach you how to do faster multiplication, how to do faster add the unit, something like that. But then they move on to design new instruction set. That's the trend for the 70s and 80s. And later, they move the focus to the CPU organization and the extension. Then we move back to the arithmetic again when we want to design better processor. And now we are in the era that we say we want to focus on GPU or virtualization or distributed architectures. Anyway, I'm gonna give you brief history up to this point. That's my goal for today's lectures before we call it a day. Got about 2 hours. Okay. All right. Again, instruction set architecture is abstractions. Abstraction. So a quick question is, if I have a document, I hand a document to you, and that book happened to say Intel instruction set architecture, for example, Intel processor. What will you see in this book? Of course, it's instruction set, right? You would see some instructions. So Intel would explain, oh, our CPU can do what? Add, subtract, lots of instructions. Because it's instructions, right? But they also say, oh, this instruction got how many operand that you can write? So usually when you write software in assembly, you say add what? Add some register together, something like that. We call this operand. Operand. Instructions and operand, like that. It can be registers, it can be, I don't know, memory, some constant number, maybe. That's the operand. And what else? You would see memory addressing. It's like when you say load what into what. Maybe this is a register, but this would be a memory address. That's the basic idea of how would you program a processor. You got an instruction, you write an instruction, and the assemblers or the compiler would translate it to machine code. which would be executed by your processor or your CPU. Okay, in reality, we also got something like interrupt. Okay, we're gonna talk about that later. And how would this translate into machine code some number, basically 0, 1, some binary number? We get to that. Okay. Well, the nice thing about instruction set is that it is a kind of abstraction. It is a kind of standard. That means you can have a new processor with the same instruction set. If I bring you back to 1964, back then, IBM was a big guy in the computer industry. So IBM would have processor coming out every year, new processor, new system, new computer system. But every computer system that come out, they got new instruction set. What does it mean? It means you buy new IBM mainframe computer, you have to trash your software and start writing new software again from scratch because it's not compatible. But after IBM released IBM 360 architectures, they eliminate different other instruction set. And after that, whenever you buy new IBM machine, you can just use your existing software. And we now in era of Intel instruction set or ARM instruction set. It means if you buy a new Intel processor, new AMD processor, your software, your Windows, your whatever operating system that you use, just work. Even though inside the computer, they are totally different design. Right? So it's how software sees the processor. You don't have to worry about what inside the system. Okay? So that means we need some kind of abstraction, and this kind of abstraction is good. Do not care about anything below that. You do not care how many transistors inside the processor. You know that it just works. If I write add, it would do some addition for me. Okay, that's instruction set. But instruction set also got point in it, which is good or bad. We will learn about it. Okay, this is how we will explain instruction set. I will use the small code, which will be written in assembly languages. Okay, I will have small code in assembly language to explain to you. A little bit about assembly language, for those of you who may not familiar. Assembly language got something that we call label on the left. And you would have instruction. And on the right-hand side of the instruction, they would say operand. So like this, the instruction is OR. You know logic OR, right? If I draw something like this, you know, right? Anything like this, you have the idea what it is, right? Okay, good. So OR, what does OR say? OR say we would OR R0, a register, with number 10. If you specify the number inside, we call it immediate. Use the number 10 in this instruction. Like that. Okay. So all these two numbers together and put the result in R1. like that. This is the anatomy of assembly programming language that we will use in this class. They got several standards for assembly language, like even for Intel, they got different standards. We got one standard for AT&T, another standard for Intel itself. Okay, we will use this notion. So let's say I want to do C equal 10 plus 20. This is how you may write it in high-level programming language like C or Python. You would write something like this. But eventually, you have to translate to something. Okay, so in this case, it's like we say we want R1 to be 10, R2 to be 20. Then let's add R1 and R2 together, put it in R3. All right, but we write in assembly language and then store it to the memory, assuming that C is at memory 100. The address of C is 100. So store it back to the memory. So one instruction that you write like this would translate into assembly language like this. 4 instructions. Okay. This is our simple CPU, our simple instruction set. So you write something in Python, in Java, in C, eventually compiler would translate it to machine code in assembly like this. But of course, if you compile it for ARM processor, you would get one set of instructions. You translate it on Intel, you get different instructions. But you got the idea. This is how it works. So you have to understand architectures then. In this case, understand instruction set architectures if you want to build a compiler. So when we have to design new instruction sets, there are several things that we have to think about. Like, oh, what kind of instruction should we put inside the processor? What kind of instruction do we need for our processor? How many registers or operand that we can specify in an instructions? Okay, how to address our memory? I put it down here. Okay. So we're gonna visit how people design the processor or the instruction set architectures. Just the concept anyway. All right. And again, to say which instruction set is good, there are several ideas to think about, several metrics to think about. I would not say that Intel is good or ARM or Apple is good. It depends. And again, one instruction set architecture that is good in certain period of time may no longer be good 10 or 20 years later. Why? Because we got changes in technologies. All right. Let's see the example. Okay. This is the Apple computer in 1977. Just want to point out that CPU is slower than memory back then. So if you want to buy Apple II computer, you see the price down here. Apple II computers. It got what? 4K of memory. For how much? $1,000. Back then. Okay. Let's try to understand this. We will explain history of instruction set. Back in the past, memory is quite fast. This is fast. And this is slow. Slow. Okay. And transistor is so expensive back then. So the architect would say, let's have minimal number of registers because it's so expensive. And memory is so fast and cheap. Just have one register then. And they call that one register with special name, they call it accumulator. Let's try simple operation. I want to do A times B plus A minus B times C, like this. Okay. Since we have only one accumulator, that means we have to put something in the memory like A, B, C. Let's put it in memory. So what do we have to do? First, we have to do what? A times B. Okay, let's load A into the memory accumulator in this case. Then multiply that number in accumulator with B. So it's like grade school, but now you can remember only one number in your head. Now you want to do A times B. Okay, let's memorize A in your head. Now times B, okay, put B in all the time, save it there. Okay. Now A accumulator equal A times B. But now we want to do B times C. We want to do B times C. That means we have to put A times B in our head somewhere else. Let's put it out. Write down as X equal A times B. Okay. X equal A times B. Then load B into your head. Multiply it with C. Now in your head you got B times C. In your head now you got B times C. Something is missing here. We have to put it out as Y equal B times C. I think I missed something here. So maybe I cut and paste from different version of PowerPoint and it got out. Then you load A and subtract it with E times C. Then you load X back in and add that with Y, which is times C. Got my point? Like that. Keep going. Simple as that. We can remember only one number in our head because our memory was so expensive back then. Sorry, our register is so expensive back then. So we remember only one number in our head. And we use memory because it's fast. Okay. This simple operation, how many instructions do we need? And just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say it's 11 instructions. This simple operation would take what? 11 instructions. Okay. Now people say, oh, maybe we don't need to remember something. Let's trash the registers, maybe. So they come up with another idea. They call it stack architecture, but okay, before we go to that, I just want to point out that, oh, it's 11 instructions. But our hardware is so small. The downside is our accumulator become bottlenecks and our memory traffic is pretty high. But if we talk about this in 1960s, we would say, oh, this is good. Okay, so we will say, okay, what about, let's not have a registers. Let's put a bunch of memory inside the processor. So left-hand side would be the processor. And we call this stack. You know stack, right? Stack, which is last in, first out. You know that. Okay, a stack. Thing that you put in, you have to take out first, last in, first out. So without stack, sorry, without registers, and we use stack. Now you can just say push A, push B. Now the stack would be like this, A and B. Right? And when you say multiply, it means you multiply two numbers on the top of stacks and you put it in. So your stack would be like what? A times B, like that. Oh, let me. Okay. You push A in, you got this. You put B in, you got this. You do multiply, you pop A and B out, you multiply them together, you put it back in. And then you put A in, you push B in, you push C in. So you got something like this. Oh, actually, it's like this. Now multiply. What to multiply? Since C and B is on top of stack, so multiply these two numbers together, put it back in. Subtract what? This is on top of stack, so subtract. Take these two out, subtract, put it back in. Now add what? These two on the top, so add them together, put it back in. Up. The nice thing about stack machine is that you don't have to specify the operand. When you say add what? Two number on the top of stacks. Multiply what? Two number on top of the stack. So you would see that the instruction would be pretty small. Unlike this one, where you say, oh, load what? Over there. Load to what? Accumulator. So this is the stack machine. Which is comparable to what the mathematicians do that. The ordering of the calculation. So with this simple operation, how many instructions count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10 instructions. Well, not bad. Ten small instructions. So this is good in terms of hardware requirement. This is good that every instruction is small. And to build the software, to compile the software, this is easy because now you don't have to translate this. If you know how to do the in order, prefix, postfix, you know that. Maybe you learned that from algorithm class. Okay, never mind. But still, the downside is we have bottlenecks, which is the stack. If we got two adders, that doesn't help because we rely on the same stack. So people say, we don't like this. Okay, now we got two types of architectures. First one is the accumulator machine, which is good for its time because the memory was fast, CPU was slow, transistor was too expensive. Okay, now we got stack machine. We say, oh, use register, just put stack in, that would be better. Then people move on and say, no, we neither need a stack or an accumulator inside the processor. Let's just use the memory directly. So CPU would be like this, only the adder, the ALU, without any register or any stack. Well, this is not bad an idea if your memory is quite fast. Okay, so we do the same thing. We want to do this kind of operation. If your memory architecture support 3 operands, so you can just do A multiplied by B, put it into K. B multiplied by C, put it into I. A subtract with I, put it into J. K add to J, put it into X. Now we just got our X within 4 instructions. Now you see my point? As we move along, different kind of architectures give you different number of instructions. You write the same piece of code, maybe in Python, maybe in Java, maybe in C. You translate it to instruction set architecture, you got different number of. This is similar, but in this case, the instruction only support 2 operands rather than 3. So you have to what? Load A, multiply it to load B, multiply it to, right? Because you can only read one number at a time. So how many instructions then if you only support 2 operands per instruction? 1, 2, 3, 4, 5, 6, 7 instructions. Still better than the accumulator machine and the stack machine. So with this kind of architecture, we can minimize the number of instructions. Right? We go from what? 11 instructions to 4 or 7. So if you only care about number of instructions, we will say, oh, the memory machine is good. But is it good? Is it really that good? The answer is, it was good back then, when memory was fast. But as the technology evolved, memory is now slower than the processor. So this is bad because this is slow. This side is slow. This side is fast. So with modern technology, we don't like this. Okay, you don't like this? This is slow with modern technology. And actually, I summarize it here. Fewer instruction, good. Easy to compile, good, but as memory is now slow, we don't like it. Okay, so modern architectures, they try to change it. One idea is, what about we have some registers rather than just one register in the CPU? Okay, let's have more register in the CPU. Again, this is now fast, this is slow. So they come up with new kind of architecture, they call it register memory. And the idea is, okay, let's put something in the register and get something from the memory. Okay. Do the same operation. How many instructions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll go back to 10 instructions. But is this a good idea now? Think about it. Still, this is not a good idea. Why? Because this is fast, but this is slow. Right? Now we want to do some calculation. One operand would be pretty fast. Another operand would be, let's wait for it. And in case you don't know, this is the Intel. So they decide that this is bad. And you just read through it, okay? Modern architecture would say, why don't we make both operand coming from registers? And we first have to load from memory, put it in registers. This is the modern architectures, modern instruction set architecture, or you may have heard of the word RISC, list, list processor. And the one that Apple use, the one that in your mobile device, it is this kind of architectures. The downside is, let's try this same operation. You have to first load, and load, load A, load B, load C. But after this would be very fast because now it's like between registers and registers, which is fast. Again, this makes sense in modern day because now CPU is faster than memory. So we say we load from the memory, put it in the register. After that, do all calculation inside the register, which is now fast. Okay, so by today technology, we should go with registers. Or sometimes people call it load store architecture because you have to load everything. Once do the calculation, store everything like that. That's why we call it load store architecture. Okay, so modern architecture is like this. So how many instruction again? 1, 2, 3, 4, 5, 6, 7, 8, 8 instruction. But we like it because it's fast. And also with modern kind of architecture, we tend to have multiple cores, multiple threads, and parallelism pipeline, basically, but we will get to that. So we will say, wow, this register architecture is extremely good when we want to do parallelism. So modern architectures, it is register architectures. So we go from accumulator machine, basically the transistor is so expensive and slow, to stack machine, which is, let's make it simple, put stack inside the processor, to memory machine, which basically say no register at all. No register at all. Let's just use the memory. To modern style processor. Let's try register. Put everything inside register first before do calculation. And we still stay with register. Okay. So anyway, if you want me to draw a timeline, it will be like this. But nowadays, like Intel decided that they would go with this, but they don't want to break the instruction set architectures. So they combine it. How does Intel combine it? Well, from programmer point of view, when you write software on Intel, you would see it's like register memory machine. But inside the processor, Intel would translate that into micro instruction inside the processor, which is a register machine. Got my point? From your point of view, you see that Intel is register memory architectures. Internally, inside the processor, internal to the processor. For every instruction that Intel put inside, it translates into smaller instruction, number of smaller instructions. They call it micro instructions, actually. Which is a list machine or the register machine. So now it just combine and they call it post-list CLAS. Now we here. Even though you see that it's a register memory machine, inside is a register machine. So that's no more debate about which one is better. Proven register machine is better. Even Intel use it now. But that also a problem in itself. Why? Because now internally to the processor, Intel use register. But outside the processor, it's register memory. So that means Intel have to do some kind of dynamic translation inside, which make it more expensive. That's why Intel processor tend to consume more power comparing to the RISC-based processor, like your ARM processor on your mobile device. That's why you do not see Intel on mobile. And when Apple decide to go with Apple Silicon, they also use ARM, which is register machine. So I don't know, maybe in the near future, Intel may be gone, I don't know. But we have some people have predicted that more than 20 years ago, that Intel is bad in terms of instruction set architectures. The x86 is bad. Yes. Oh, if you look outside the processor, from the outside, this is the Apple machine, which is the kind of list. It's based on ARM. ARM instruction set architectures. But AMD from the outside, it x86 64. Same for Intel, anyway. From the outside, it's register memory machine, so we call it complex instruction set. In a sense. But internal to the processor, they translate it into register machine. So you do not see it. Do the same thing. I mean, same idea, but they do different kind of implementations anyway. But you may know that Intel is going down in market nowadays. You happen to know why? Why comparing to AMD now, Intel is on the downside.
As all the AI chips are there, like NVIDIA, for example, like they didn't get more.
Yeah, that's one reason. But I mean, internally, Intel also have issue with some kind of technologies. Like now, AMD can do, I cannot remember, 1 nanometer, something like that. Intel still struggle with 2 or 3 nanometer, something like that. And the pipeline inside, the structure inside, they still fail to do high-speed bus. Like if you use a server with Intel processor, the PCI bus would be slower comparing to the AMD counterpart. So Intel have some problem that they have to catch up, and they fail to catch up in time. Which in the past, historically, if you don't know, Intel was the first company to make good processor, good clock inside the processor. And Intel said, we want to sell this processor to the Army, the United States Army, the United States government. Back then, the United States government said, we will not buy Intel processor unless Intel allow another company to produce similar kind of processor. Why? Because the government say, should something bad happen to Intel, we got nothing. So the government told Intel back then, Intel, you have to find another company that make compatible processor. For that, something bad happened to Intel, we have alternative source. That company happened to be AMD. So originally, AMD was like a company that have to follow Intel, or else Intel cannot sell product to the US government. But nowadays it's the opposite, right? AMD can do some better, can do something better than Intel. So Intel failed in a sense. Okay, but it doesn't mean that if you use an Intel processor, you have to sell it. No, that's not nothing to it. But if you buy a new one, AMD product tend to be faster than Intel. You can still buy Intel. Intel still offer best price to performance. I mean, in terms of power consumption, it's still better than AMD. But if you want better performance, you have to go with AMD. Okay, I'm not a big fan of either Intel or AMD. It's up to you. Or Apple, you can buy whatever you want. But from architectural point of view, I would say Intel and AMD would use more power comparing to the pure register machine like Apple. So you can compare the battery life. Fully charged, Apple would stay like, I don't know, a day. While Intel laptop would stay like less than half day, something like that. So whenever I carry Intel laptop, I have to make sure that I got some power that I can plug in. But for Apple, I can just take the machine and use it the whole day. That's the difference. Okay, just pictures that put them all together. Okay. This is on the CPU side. This is on the memory side. So back then, it's this simple. This makes sense when memory is faster than CPU. But now, this is the best. For parallelisms. And that's also show up in calculation in the number. Okay. So again, two paradigms, complex instruction set and reduced instruction set. Now, reduced instruction set is better. Intel was a complex instruction set, but now it's dynamically translated inside. So we call it POSIX. ARM, the one that the instruction set that you use on your mobile and the one that Apple use it, actually is Acorn RISC machine, ARM. That's why we call it ARM anyway. All right, that's quick history of the instruction set design concept. Still okay? Not too much, right? For a day, or too much already. Okay. Another idea. Memory organization. There are two concepts that you have to understand. Ordering or endian. The word is endian, E-N-D-I-N, endian. And alignment or parallelism. Okay. We will try to understand endian and alignment. All right. Well, we know that 1 byte got 8 bits and some kind of variables. It's multiple bytes variable. Like in C programming, character would be 1 byte, short would be 2 bytes, integer would be 4 bytes, long means 8 bytes, float would be 4 bytes, double would be 8 bytes, and long double would be 16 bytes. Okay, so that means you have to write them in order somewhere if you want to represent something that's larger than a byte. Let's start with ordering. or Indian? Well, there are two ways to write it down. Let's say I got some number. Maybe it's base 16, okay? 1, 2, 3, 4, base 16. หาร16 base 16. Or another way to write 1, 2, 3, 4, base 16. Okay. But programmers usually try 0x, mean base 16. Hexadecimal. We got 1, 2, 3, 4, base 16. That would need what? 2 bytes. Right? ทันมั้ยเนี่ยงงไหม Because this is 8 byte, this is 8 byte, so this is 2 bytes. Okay? Base 16 mean one number need 4 bytes. So 2 number need 8 bytes. I got 4 numbers, so I need. Sorry, base 16 mean one number need 4 bits. So 2 number is 1 byte. So I got 4 number, that would be 2 bytes. Okay? So let's say I got 2 memory. First one is 40. Second one is 41. 2 memory, 2 bytes of memory. So there are 2 ways to write this number. You can write it like this. 1, 2, 3, 4. Or you can write 1, 2, 3, 4. Got my point? See the difference? To get this 16 base 16 number with 2 bytes, I have to read 2 bytes and put them together. But when we put down in memory, there are 2 ways to put it. This one and this one. This is lower address, 40. This is higher, 41. And they just name it. They name something like this. Big Indian. And they name this Little Indian. Big and little. So let me give you an analogy to this. Maybe you understand. Since we use Thai language, we write from left to right. But some language, they write from right to left. Okay, so if you have some number, like you have 1025, we learn to write it this way. But in some languages in the past that go from right to left, they would like this, right? Got my point? Let me clarify that in Thai. บางภาษาเขียนจากซ้ายไปขวา บังเอิญเราใช้ภาษาไทยเราเลยพูดจากซ้ายไปขวา แต่มันมีบางภาษามันเขียนจากขวาไปซ้ายเนี่ยถ้าเกิดคุณบอกคุณจะเขียนเลข125 คุณเขียนจากซ้ายไปขวาหรือคุณเขียนจากขวาไปซ้าย Same thing. Change that to computer. you got page, you have to address the byte. This is number 40. So next byte would be 41, next byte would be 42, and so on. So you write what? 1, 2, 3, 4, or 1, 2, 3, 4, like this. They have different name for it, little endian and big endian. Or one way to remember is that little endian mean low order byte stay at low address. So this is lower order byte, least significant lower order. ก็เข้าใจคำว่านัยสำคัญต่ำกับนัยสำคัญสูงใช่ไหมนัยสำคัญต่ำ least significant stay at lower address. Higher significant stay at higher address. ขอโทษ sorry I just see that I write it wrong, so it should be this. Sorry, this has to be big. Sorry, readไปหน่อยครับ This has to be little. Sorry. Low or least significant stay at lower address. So this is least significant, so it stay at lower address. Sorry. เมื่อกี้รีบเขียนไปหน่อยกลับข้างขอโทษ But if you put high order byte at the lower address, we call that big endian. So Intel say we go with little like this. So that means the first byte that you read would be the least significant. And you move to the next address you read, you got more significant and so on. เหมือนหลักหน่วยอยู่ที่เลขน้อยบังเอิญเลขน้อยเราไม่ได้เขียนซ้ายมือตำแหน่งเรานับจากซ้ายไปขวา0 1 2 3เนี่ยตำแหน่งที่0เลขนัยสำคัญต่ำตำแหน่งสูงขึ้นนัยสำคัญสูงนี่แบบ Intel okay and big endian on the left we start with low address we write high order with more significant. So you read the first byte, you get the high order. This one is used by ARM or IBM PowerPC or several processors use big endian. I would say only Intel use little endian. I'm not saying which one is good or bad because it's trade-off. Why it is a trade-off? Because when you add two numbers together, usually you start from least significant and you put the carry on and do the more significant. ถูกไหมเวลาคุณบวกเลขคุณบวกสักหลักนัยสำคัญน้อยไปมาก So on Intel, the first byte that you read, you can do the calculation right away. But if you do comparison, if you first start with high order, you read the first byte, you know right away which one is larger. นี่ออกไหมฮะถ้าเกิดว่าคุณอ่านนัยสำคัญสูงก่อนคุณอ่านปุ๊บจำนวนไหนมากกว่าอ่านเสร็จรู้เลยมันเครื่องหมายบวกกับเครื่องหมายลบต่างกันตอบเลย So it's not which one is better, it's just different way of representing. Actually, this is the nice picture of it. This is the hex number. Okay. 1A, 2B, 3C, 3B. Okay. So little endian means lower address is least significant. This is the least significant. Right? Big endian means lower address. You got the more significant. Just a way of stalling thing when we have multiple bytes of data. But what make it more complex is that sometimes, even though like Intel architecture, it is little endian, but the file format is big endian, like you use Photoshop files, some kind of image files. They always go with big endian. So when you do Photoshop on Intel, you read the files, you have to swap the order before do the calculation. Well, there was a reason for that because Photoshop first available on Mac only. I mean, 20 years ago, 30 years ago, we got no Photoshop on Intel processor. So they designed the Photoshop files for Apple, which is big endian. Later, Intel processor got better, so they want to use Photoshop on Intel. So they use the same files, different processors. They have to change the order in the process. Okay, I'm not saying which one is good or bad, just trade off. You have to pick one, just like that. All right. Just to show that with little endian, you want to add to number, let's go like this. Right, 1, 2, 3, 4, like this. But if you want to know which one is greater, you have to read 1, 2, 3, 4, and then you can compare. It take longer for little endian. Okay, but for big endian, oh, just read the first byte. I know which one is greater. Done. But if I want to add 1, 2, 3, 4, then add 4, 2, 3, 2, 1. You inverse order. Just design trade-off. Okay. Okay. That's the endian thing. We will try another concept, memory alignment, and maybe I stop here because it might be too much for you for a day. I can see that you are now silent and oh no, I'm in trouble. Okay, let's try to understand memory alignment. Well, back then, when we connect the memory to the processor, we use the 8-bit bus, 8-bit 8-line to reading the memory. So this is when you read something, you got 1 byte in. When you read something, you got 1 byte in, like that. You know how memory works, right? Memory is like this. You put in an address, you got a data, right? Data. So you put in an address, you got data. Now say you want to make it faster. How? You parallel the memory together. You put in the same address, but now you got what? 2 bytes of data. Parallelism. Share the same address. Like I say, hey, I want the first data. You say you give me 1 byte. I say, I want to read faster. So I got 2 memory. I say, give me the first data. You give me the first, you give me the first. Now I got 2 bytes at the same time. This picture basically. So back then, 1 address at a time, you get 1 byte or 8-bit. Modern architecture, I put in one address, I got more than 1 byte. In this case, it's 16-bit. Well, nowadays we got what 16-bit processor. That means I put one address in, I got what 8 bytes. Parallelism in a sense. That's why modern processor is faster, because one read means several bytes. In the past, one read, just 1 byte. Okay. Got my point? This is the low-level hardware. One address got 2 bytes. In the past, if I want to read byte number 1 and number 2, I need 2 cycles. First cycle, I got this. Second cycle, I got this. Right? Nowadays, I want 2 bytes. 1 cycle, I got 0 and 1 within 1 cycle. Got my point? In the old day, this is 2 cycles for 16-bit. Right? Nowadays, 1 cycle for 16-bit. 2 bytes. 1 cycle, 1 byte. Got my point? So that means if your number kind of align to this, you can read that number within 1 cycle. But if your number is not aligned, that means you need 2 cycles, first one and second one, and combine them together. Got my point? Let me give you a real world example. Let's say I can take maybe 2 seed person from these 2 seed in the same row at the same time. So I say, hey, first row come in, so I got 2 person. Second row come in, I got 2 person, like that. Okay, now what if data that I want to read, first byte flat, second byte is empty. I say I want my number, so I have first cycle, hit this byte. Second cycle, takes the byte, combine them together. But if my number say this is the first byte, this is the second byte. First row come on in, now I got 1 number within just 1 cycle. Okay, the kind of bus of memory organization. 1 row in 1 address. Got how many bits? 2 bytes in this case. Okay, so what we should do is that always make sure that our data is on the same row. That way we can read it faster. We call that alignment. So let's say I got some variable in C programming language. I got integers for A, integer for B, integer for what? B1, and double for C. Okay. Integer is what? What is the size of integer? Oh, okay. Sorry. Where's that? Where's that page? Sorry. Oh, sorry, this page. Integers is 4 bytes, 32 bits. Okay. Double is 8 bytes, like that. Okay. And now we got integers, and double. If in this case is each row is 4 bytes, so I got integers. I should skip a little bit before I start with double. So I can read double better. Got my point? Minimize the number of read cycle when you want to read in something. Okay, maybe I tweak the example a little bit. Okay, draw something. Let's say I got a character A and integers B. Okay. Okay. And I got memory like this. Let's say one row I got 4 bytes, 32-bit architectures. Okay. If I want to do standard memory allocation, it would be A goes here and B goes here. Right? A for 1 byte, B for 4 bytes, 16 bits, sorry, 4 bytes, 32 bits. Which is bad because now if I want to read B, I have to take 2 cycles. 2 cycles for B. Okay, so another way to think about it. What if I put A here and I put B here? Now I can read B within 1 cycle. Okay, better. We call this kind of architecture restricted alignment. Which is in the slide, actually. Restricted alignment. That means you have to, well, put in some space in exchange for being able to read some number faster, read some variable faster. But the downside is like this. Well, technically speaking, you would say, oh, this is 1 byte, this is 4 bytes, so we only need 5 bytes of memory. But with restricted alignment, oh, this is 1 byte, what? Wait, we have to do the alignment, so this would need 4 bytes of memory. So it's 5 bytes versus 8 bytes, but faster. Am I right? Of course, new architecture would prefer to go with less stick alignment because it's faster. But older architectures, Intel, for example, may go with unrestricted alignments. Or Intel can do either restrict or unrestricted, but I would say Intel is unrestricted alignment. But if you do the alignment, it will be faster. Okay. So that's why some program would use more memory in exchange for better performance, being able to read faster. Right? So unrestricted alignments, it's easy to write software. Restricted alignment, burden on software, or in this case, compiler. But it's faster. And you may not know, modern processor like modern day Intel's, the best performance is 16 bytes alignment. 16-byte alignment. So there is a reason behind that, but well, it would take an hour just to explain that. And when Mac decided to go with Intel processor, the Mac Intel processor, the same program running on Mac would use more memory because Mac do not have legacy code. They go with 16-byte alignment right away. And Windows doesn't enforce alignment in software, so use less memory, but maybe slower by design, okay? Okay? Still good? Sure? So we go with alien and then alignment. You want to try this? Addressing mode. Okay, let's try addressing mode. I may revisit this again next week, just in case you don't understand, because we also use a lot of addressing mode anyway. Addressing mode basically means how would you specify data in the operand? Okay, start with something simple. You say you want to add number 4 or assign number 4. We should be able to specify number 4 in our instructions right away. We call this immediate. Just put whatever you want, some number, put it in. That's the first addressing mode. Most architecture have it, immediate. Second mode, register direct. Okay, I want to add B and C, so specify B and C and the result A. Then register direct. Next mode, displacement. Okay, let's take a look at these data structures. Okay, if G is a variable. That means the first 100 bytes of G would be name for 100 bytes. And if you want age next byte, it would be 100 place away from the original place, right? Because this is 100 bytes. For name, it starts with 0, so it stops at 99. Age character, just 1 byte. At byte 100. So you have to specify that I want to address G. It would be 100 bytes from the beginning. Displacement, it means add 100 to this. Then read it. We call this displacement. This is the displacement number 100 in a sense. So when you write software in C or in Java or in Python using the objects, it's always a displacement addressing mode. I mean at lower level. Same thing for an array. You hard code the index to 100, but that's basically 100. But if index is a variable, we call it register indirect. This is basically a pointer. If you know pointer in C, this is pointer. Register indirect. And this is base and index, or sometimes we just call index. In a sense, index is just a variable. So different is displacement index is an immediate value. Index means index is another variable. Okay, direct, just put the address in. And memory indirect, it means a pointer to a pointer. If you know C programming languages, auto increments, it's like this. Similar things, auto decrement. And scale, I mean, you do some calculation, like since integers is what, 4 bytes, so you want integer I, so it's I times 4, then add it back. This is addressing mode. Basically how you specify data inside the memory. See that when you write software, you use variables, but when we translate it into machine code, it's just memory. Variable is just a memory, so you have to calculate where is my memory or where is my variable. We still on the same page? Okay, good. Question. Do we need all of them? No. So which one do we actually need? Immediate, we need it. Register direct, we need it. Do we really need index? Well, actually, we can do register indirect and live with it. We can live with just 3 addressing mode. That's my point. 3, why? Because if you do the calculation first and you put it in R2, it would work, right? Okay, let's try this. Let's say we only have immediate register direct and register indirect. It's like that. Now I want to, let's say, emulate displacement, what do I have to do? I have to first add R2 with 100. Then I can load R1 with R2. Right? That would give me displacement, but with 2 instructions. Got my point? If we got only 3 addressing mode, technically speaking, we can translate every other addressing mode into register indirect, but it would take more cycles, more calculation. Meaning you calculate the address first and then read from the memory. But if we have displacement, oh, it's just 1 cycle and I get the data right away, faster. So the whole addressing mode means if you can make the processor run faster, I mean, can calculate the address within the same cycle. Perfect, that's faster. If you cannot, still slow. So other addressing modes just make it faster. But if we ask for necessity function, I say 3 addressing mode is enough. Now you see, so far I have presented you several choices. Endian, you decide an instruction, what kind of endian should I choose, big or little? Alignment, should I do holistic alignment or not? Right? What else? Addressing mode, how many addressing mode do I need? We have decided we will go with digital register, so we will not make a choice on that. What else? So many choices, actually. That's why designing a processor is difficult, because you have to trade off for several factors. Okay? And statistically, maybe we need just 3. But people say, oh, having displacement would be faster. Okay, let's put displacement in, because people like it. People use it a lot. So maybe we have displacement immediate, register indirect, and register direct. Done, 4 modes. That's more than enough. Okay. And the next question is, maybe that would be the last slide for today. Next question is, oh, sorry. Go. Next question is, okay, we say we want to use displacement. The question is, how big is the displacement? How many bits should we use for the displacement? So to answer that, we do some analysis of the real software. And we say that, oh, with displacement, most software would go with, I don't know, maybe less than 16 bits. So if we allow 16 bits of displacement, maybe that's enough. Similar questions. Immediate. What size of immediate should we need? And again, we do the analysis and we say, oh, most software would go with what? 16 bit maybe, or 8 bit, less than 8 bit of immediate. Right? Because if you allow big number of immediate to put in an instruction, you would have bigger instructions. That would be more expensive, of course. Okay. All right. I think I stop here. And next week, we're gonna continue with the instruction class and the control flow. Okay, and the interrupt. All right, any question about today's class? Too much already, ready for lunch. Again, try not to skip the class or miss the class. I can help you a lot in the class, but if you not show up, I don't know which part you do not understand. Okay, but in class, if you ask me, I can always answer anything. Okay, let's call it a day. Go enjoy your lunch. I post the video later today. Thank you.